We are on the subject of differential equations. We start with defining what is a differential equation. Then we will cover the definition, the meaning of equation, and particularly the meaning of a solution, its geometrical interpretation of the equation and solution, order and degree of differential equations, and finally we will see types of solutions. So let us start with defining a differential equation. Any equation that contains derivatives and the dependent, independent variables, derivatives or differentials, is called a differential equation. We'll take a very simple example. This is a very simple differential equation. dy dx is equal to 2x. Now, we will get back to this equation in the context of the geometrical meaning of differential equations. But before that, this is a very, very simple differential equation. Some differential equations can be written in the form m dx plus n dy is 0, where m and n both are functions of x and y. We will get back to this equation when we are discussing integrating factors. Now, let's start with this particular equation and see whether we can get some extra meaning, and then we will come to a conclusion about what exactly does a differential equation describe. We have learned in high school that when we have dy dx is equal to 2x, this implies that y is equal to x square. I am purposely omitting something which we'll get back to later. Let us start with a function y is equal to x square, and this implies dy dx is equal to 2x. Now, there is something incomplete here, because when dy dx is 2x, y must be equal to x square plus some arbitrary constant of integration. Constant of integration has to be put, because if I differentiate this, evidently dy dx is going to be 2x. Now, we will draw the shape of the curve y is equal to x square and come to one geometrical conclusion, and that is what the differential equation says. We have written y is equal to x squared, and this is graphed as a parabola that is symmetrical about the y-axis. This parabola is symmetrical about the y-axis, and all that this equation says is as follows. If I take any point on this parabola and draw a tangent to the curve at that point P, then the slope of this tangent is 2 times the x coordinate of that point. And the differential equation says that whenever we are on this parabola y is equal to x square, the slope is 2 times x coordinate of any point on that curve. It is not valid only for a single point or a few points, it is valid for any point on that curve. So that is the geometrical property that is contained, and we can say that in general a differential equation does give some geometrical property of not a curve, yes, but a family of curves. That is contained in the next step. When we come here, we start with this and try to solve it. We write, as we did before, y is x square plus c. Now this C, actually it means that you know this property that the slope is twice the x coordinate can be extended to parallel parabolas. So this is the value of one C. You can have a negative C, that means another parabola which goes like this. For any particular x, the slope is equal to twice the x coordinate. In other words, the tangents here, here, and here, they all become parallel to each other. These tangents have the same slope, so they are parallel to each other. So in other words, we can summarize that a differential equation gives either an explicit geometrical property or perhaps not easy to interpret geometrical property. And the solution leads us not to one curve but to a family of curves which is taken care of by the constant of integration that may arise. Now we come to the order and the degree of a differential equation. First, let us start with order. A differential equation is expected to have derivatives of different orders, the first, second, third, and so on, nth order also. So order is defined as the highest order derivative that is contained in the equation. The highest order derivative that is contained in the equation is called the order of the equation. For example, let's take this. This is the differential equation. The highest order derivative available is d2i dx2. So this is a second order differential equation. When we come to the degree, we go and inspect the index of the power to which the highest order derivative has been raised. Here it becomes just d2i dx2 to the power of 1. So this is called a second order but first degree differential equation. However, if we change this equation to, for example, this 3 or 2, then it is a second order but third degree differential equation. Second order but third degree because the degree of the highest order derivative is 3. So there is one comment which has to be remembered, and that is important to say that we, while trying to find the order and degree, we have to write it in polynomial form, bereft of all radicals. Bereft of all radicals. I'll give a simple example to find the order and degree. We write it in polynomial form. One more example. We have learned in some form or the other in differential calculus that the curvature of a curve denoted by kappa is d2y dx2 divided by 1 plus dy dx whole square to the power of 3 by 2. That is known to us. The curvature at any point on a curve is denoted by kappa is d2y dx2 divided by 1 plus first derivative whole square to the power of 3 by 2. Now this is again a point by point phenomenon. That means the curvature will vary from point to point because d2y dx to the value of the second derivative as well as dy dx, they all keep on changing with the position of the point on the curve. Now, if we simplify this, we can write k 1 plus y1 square to the power of 3 by 2 is d2y dx2. If care is not exercised, then one comes to the conclusion that this is a second order first degree equation, which is not true because we just said that it has to be bereft of radicals. In other words, we have to square both sides. If we square both sides, we will get this to the power of 3 is this to the power of 2. In other words, it is a second order second degree equation, not a second order first degree equation. We now come to the last part of this lecture, and that is the types of solutions. There are basically three types of solutions to a differential equation in a broad category. I write them out. One is called the general solution, or it is called the complete primitive. Complete primitive. Second one is a particular solution. Third is called a singular solution. These are broadly the three categories of solutions. One, the general solution, which is also called the complete primitive. Second, particular solution. And third is a singular solution. Now we will run through these very briefly so that we form an idea. First, let us start with general solution. The general solution or the complete primitive is defined as that solution which has as many independent arbitrary constants as the order of the equation. I repeat, a general solution or the complete primitive is one which has as many independent arbitrary constants as the order of the equation. We'll take an example. Here we have something called a simple harmonic oscillator, in which we have a mass, a block of mass m attached to a spring, and the other end of the spring is fixed to a wall. We assume that there is no friction between the block and the bottom surface. So here we have no friction. Now, if this block is pulled a little to the right and released, then it will start oscillating about this mean position, which can be indicated from the origin by a distance x. X is the distance of the center of mass from the 0 point. This is x is equal to 0. Okay. Now, in any standard book on physics, it can be found that the situation, the vibrations can be modeled by a simple equation which, using the dot notation, where omega square is called K by m. K is the spring constant in appropriate units. So x double dot plus omega square x is equal to 0, and the buck will go backward and forwards, and actually these oscillations, unless there are external damping forces, they are supposed to go on till doomsday. That means they will never stop. So this is another way of writing actually d2x dt2 plus omega square x is equal to 0, of which we know that a solution is given by x is equal to a cos omega t plus b sin omega t, or you can write C1 cos omega t plus C2 sin omega t. C1 and C2 are written to re-emphasize that there are two independent arbitrary constants, and it is very important to understand the meaning of independent arbitrary constants. That means there is no linear combination of C1 and C2 which can generate 0. In other words, it will not be possible to find any lambda or any mu such that this is 0. So this will always happen. Lambda C1 plus mu C2 will be equal to non-zero. Now, this is therefore the general solution for this particular situation. We come to particular solutions. After that, after general solution, we had particular solutions. Now, particular solutions are derived from the general solution by doing what? By assigning particular values to the constants. So, for example, if we took say C2 or any of them as 0, x is equal to, we could get C2 sin omega t. This is a particular solution. I can give a particular value to C2, 5 sin omega t. Actually, these particular values are reflective of the initial positions at time t is equal to 0. So that is the particular solution which is derived from the general solution by assigning specific values to the constants of integration. The last type of solution we are going to discuss right now is called the singular solution. Singular solutions, I'll give a definition and then take an example. It's a very good example and is a way of understanding the singular solutions very easily.